All right. Okay. Good afternoon, everyone. Today will be last lecture. Okay. I hope I can finish things needed for homework and final exam. Okay. In case not, I may give you some short videos other than the last one. Okay. I hope I can finish everything, but actually need to cover a lot of material. Even playing the graph itself will take a week or two at least. Okay. So I can just give you a very get some feeling about planar graph. So today's main topic is planar graph. All right. The importance of planar graph is obvious. For example, if you look at this graph, can you tell what this graph is? The way we draw it? Not easy to see, right? Okay. Okay. So this statement again. Okay, you try to make it as simple as possible. Okay. Oh, here, by the way, that's English translation in Chinese. This English translation, actually. Okay, actually, for English translation, I like this translation, KISS, or this one. Keep it simple, stupid, okay, but it's not, may not be appropriate for all situations. So for this one, can we got a simpler way so that we can easily see what this graph is? One good answer is to use a so-called plane embedding. If we draw a graph without edge crossing, then it's maybe easier to, usually it's much easier to see if edges do not cross each other. So here are a lot of crossings that makes things difficult to see. So actually, use this one, we can easily draw it. Use this guideline. I posted some guidelines for doing homework for graph problems yesterday. Take a look at these general guidelines. That will be quite helpful. Okay. As detailed as a hint, I will give some hints to you. Okay, maybe not today. By Friday, I want you to think first, then I give you some hints. All right. So that's called a planar graph. It's a planar embedding of this one. This is the same graph. But if I draw it in this way, it's very easy to see what this graph is. But with drawing like this, it's difficult. Convince yourself these two graphs are really the same. Okay. So today we mainly focus on planar graphs, how to draw a graph on the plane so there's no edge crossing. Of course, at vertices they intersect. Other than vertices, they have no crossing at all. All right. Such a drawing is called a planar embedding, and the graph we obtain is called a plane graph. So the graph, particular embedding of a planar graph is called a plane graph. So that's a plane graph of this graph. This graph actually is planar because it has a planar embedding. So this particular planar embedding is called a plane graph. All right. Now, so what we are going to touch, actually, the main thing we are going to touch is number of edges in a planar graph is at most 3n minus 6, whenever n is at least 3. Whenever graph contains more than 3 vertices. So we cannot have too many edges in a planar graph. All right. So in case a planar graph has no triangle, number of edges is even less. So in terms of the number of edges, planar graphs are relatively sparse. All right. So then we are going to present the following very beautiful characterization of planar graph that exactly characterize what under what situation a graph is a planar graph. So that characterization is closely related to these two particular graphs, K5 and K33. So it says a graph, Kowalski theorem says that a graph is a planar graph if only if it does not contain this graph or this graph and subdivision. I will introduce this notion later, okay, subdivision. And the subdivision, so basically without these two graphs, then the planar graph, then the graph will be a planar graph. Okay, so that's the main thing we're going to discuss today. All right. Okay. All right. So we'll start. A plane embedding is a drawing. So we draw a graph on the plane. So there's a plane. Okay, so whiteboard is a plane. All right. So we draw the graph on the whiteboard. We have vertex corresponding to points, and edges are curved. All right. So that's a plane embedding. So vertex will be mapped to a point. Of course, if it's just a point too small to see. If it's mathematical point, it's almost impossible to see it because size is infinitely small, so it's not zero. Okay. So typically we draw a circle of a little bit larger in order to illustrate it. And the edge will be mapped to a curve, any curve, not self-intersecting curve. So curves should not be self-intersecting. Okay. So that's a little bit topological stuff, non-intersecting. So it should not cross itself. It can be very complicated, but typically no need. Typically no need to draw such curve. Typically, actually in practice, it's almost a straight. It can be a straight line. Actually, it's always actually there are always ways to embed it so that like the curve linking that actually is a straight line. Of course, in practice, sometimes may not be a straight line, right? Go like this because we do not arrange these points very carefully. Then sometimes we need to do things like this. But if we really do arrange points very carefully, it can be always a straight line. Okay. So such a drawing is called a plane embedding. If the following condition satisfies. So it's a drawing of a plane such that edges do not intersecting on edges. So such an embedding is called planar embedding. All right. The keyword is planar, the embedding planar. All right. So this one is a plane embedding. And the graph way of plane, as I explained before, is called plane graph. So this one is not a plane embedding, but this one is. So this one is a plane graph, but this one is not a plane graph. All right. So not every graph can be drawn in this manner. For example, if we try this graph, this complete graph, so let's get a feeling why some graph cannot be drawn in this way, in a planar way. All right. Typically, this problem will be posed as a puzzle. Typically, three houses, then three different utilities, gas, maybe electricity, water. You have to link them to these three houses. But these lines, electronic line, pipeline, water pipeline, they should not cross each other. Typically, it will be posed as a puzzle. All right. So let's see how can we draw this one. Of course, the drawing of this one is unique. Regardless of how we draw it, it look like this. So if we delete one vertex, then any drawing will look like this, basically. All right. Now for one remaining vertex. Now, if we look at this drawing, once we have a planar drawing, these curves will divide the plane into regions. So these line edges or lines divide plane into regions. As a plane, okay. Regions. All right. So each region is called a face. So this region is called a face. So a plane embedding will divide the plane into several faces. So in this case, one face two face and three face, outside one. Always there are outside one. The exterior one or external one, exterior face or unbounded face. There are different names for the outside one, the largest one if you want. Okay. So this drawing will divide the plane into three regions. Now the fourth point, the last point, say this point. All right. So we can put it outside of this one or this one. So anyway, it's inside the region. So actually it's symmetric. Whether outside of this one is symmetric because let me explain why this even outside one is same. Because actually embedding a plane is same as embedded on the sphere. It's exactly the same. If I embedded the whole thing on the sphere, like the Earth, surface of Earth, then this face is nothing more than these faces. It's basically the same. All right. So it's a symmetry, so we can just actually take a point inside here. Now this one to this vertex must be joined to these three vertices. So these two, of course, no problem. But this one, this point is inside region, this point in the outside region. There are curve, close the circle here, separate this region and this region. In order to draw a line from this one to this one, I have to cross some edges. That is the bound of the cycle. So I can draw it in this way, so cross this one. Or I can draw it in this way, cross this one. I can draw it in this way, it's a cross. All right. So that's the intuitive idea. Actually, that's hardly serve as a proof because dealing with topology is very, very difficult. So one have to be very, very careful. But this will illustrate the idea why this one cannot be drawn on the plane without edge crossing. So we don't have plane embedding on this one. Similarly, we can do this for this one. All right. Okay, so we're just reading about plane embedding and plane graphs. So now once we have a plane embedding a plane graph, some plane is divided into phases. Like this one is not planar, so we cannot talk about phases. But once it becomes planar, we can talk about it. So how many phases do we have on this one? Inside there are 1, 2, 3, 4, 5, and there are outside 6 different phases. So if we construct a new graph, where its vertices are faces of the plane graph. So each vertex, each face will be a vertex in the new graph. Okay. Then for two faces, if they share an edge, then we add an edge. If they share an edge in here, if they say if these two faces share a common boundary, then we add an edge. Okay, so we get this graph. Inside it looks like outside. Now, third one, for each bounded share, we add an edge. Each edge is shared. So this one share this edge, this face, this edge, share this edge, we add this edge. And this face, I'll share this edge with this face, we add this one. Add this one, and also add this one. So that graph we obtain is called a planar dual. I'll just say dual graph, maybe it's easier. This graph is a dual graph of G. Of course, it's also a planar graph because it's the way we draw it, we see it's a planar graph. It actually gives us a planar embedding. So such a graph is called a dual graph. All right. So be careful for this one. Now, for this planar embedding or planar graph, there are two faces. One is here, one is outside. All right. So for this face, there are three edges. They share three edges. So each edge will have this. Now for this edge, actually what we'll do is create loops. This face, exterior face, share this edge with itself, then what we do, we draw a loop. So the dual can contain multiple edges and loops. The dual may contain multiple edges and loops. So when it does not contain a loop, it's when it has no cut edge. When it has a cut edge, it always has a loop. If it has a cut edge, it always has a loop. So that's why the cut edge. So we draw it in this way. It has no loop only when when it has no cut edges. All right. But anyway, we have a notion of dual graph of G. All right. So that can be obtained in this way. Now another notion is the length of face. How many edges in a face? Of a face, maybe. The face length defined to be number of edges of a face. So that seems to be very, very simple. All right. So for example, this graph, we have four faces. It's quite easy to tell. So this face has three edges. One, two, three. This one, two, three, four. This one, two, three, four. Outside is five. That's very easy to tell, right? In this particular case. However, there is an exception when there are such edge or the inside is one face, but we may have this one. So for this one, how many edges? What's the face length of this one? It's not four, okay? Technically, what we need is close the walk bounding the face. Number of edges, enclose the walk bounding the face. The face length of this one is not four, but eight. So for this one is eight. Close the walk, 1, 2, 3, 4, 5, 6, 7, 8. Outside one will be 7. Here 5, 2. The outside one instead of 5 it becomes 7. So be careful with that technicality when we determine the face length. Okay, this cut edge will be counted twice when it's a cut edge. So let's see if you understand the meaning and definition of face length. Okay, so we have three faces. This one is 4, very simple. This one is 3. What's the face length of the exterior face, external face? The correct number is 9, because this one counted twice. The face looks like this. Okay, so now we are ready to prove Euler formula. For any planar embeddings, there are a connection between number of edges, number of vertices, and number of faces. So that is summarized in the formula called Euler formula. So now we are going to prove Euler formula. All right. So our formula says for any connected plane graph, it's important to have condition connected. Otherwise, this one does not hold. Of course, if we add the number of common components together, we can generalize this one. All right. For any connected plane graph, number of vertices. So here is vertices. N is vertices. M is edges. And F is number of faces. So they satisfy this condition. All right. So let's take a look. For this graph, number of vertices is 8. Number of edges is 12, right? Number of faces is 6. 14 minus 12 is equal to. So that means regardless of how we embed it, as far as it's planar embedding, we always get same number of faces for any planar graph, regardless of how we embed the graph on the plane. The number of faces is always fixed because of this formula. So this one is very, very fundamental. Many results on planar graph can be obtained more or less we use this one to obtain a result. I will give you a hint later for homework problem. Okay, perhaps not now. So why this one is the case? There are many ways to prove this one. I don't think I'm going to give you rigorous proof using induction. Actually, the idea is already there, but I will give you at least 2 different ways to feel it. Why is this the case? Actually, both of them can be used as an inductive proof. All right. So why number of faces, number of vertices, and number of edges will satisfy this condition? So actually, maybe extreme condition. The extreme case, or even the extreme case, a single vertex. What happens? One vertex, edge 0, face 1. So in this case, we see this number. C number adds to 2. So in the extreme case, C number adds to 2. That's how we get this number 2 initial value, somehow initial value. All right. So then why in general we have this condition? So we can look at things recursively or inductively in 2 different ways. All right. So let's see. First way is maybe in terms of cycle. So a cycle with n vertices. All right, then of course this cycle can have m edges. So embedding of this one will have 2 faces. Number of face will have so m edges here is also n edges. Number of faces is 2. So we use this one as it's a basis case. So then we see that again n minus m plus f equal to, because these 2 cancels, right? Same thing. So one is to see from this point of view. If they are cycles, then we get this one. Now, how do we form planar graph? So actually, any graph can be obtained, any planar graph, except when it has no cycle. So we just add a path. Any graph basically can be formed by add a path. So gradually we keep on adding paths, eventually form the graph. If it has cycle, okay. Otherwise, we go to another one, another intuitive thing. Okay, so once we have this cycle, how many vertices we add? So let me make it simpler, maybe just 2. All right, so we add one more vertex, two more edges. So by doing that, we create one more face. All right, so difference here is 1. The difference between number of vertices and edges is 1. So here, we increase difference by 1, and the face will be increased by 1. So that 2 will not change. Increase this one by 1, increase this one by 1, minus plus, they cancels. So after this 2 really play important role. If we keep on doing that, nothing changes. So this number still maintained. So we keep on doing things. All right. So if we get our pin graph in this way, we can see it's always holds. So that's the intuition we can use induction based on this one. But of course, you may say, what happens if a graph has no cycle? Then we cannot use this idea. If a graph has no cycle, right? For this kind of graph. That's called the tree, right? The tree is a connected graph without cycle. For this kind of graph, we cannot use this argument. But indeed, we can always start our induction with this one as a base. If you don't want cycle, then we can always start with this one. Because even if a cycle, if we delete an edge from cycle, we get a tree. It's a path, which is a tree. So another idea is just to start with a tree. So for a tree, what we have. So suppose we have a tree, what we have? Number of vertices in a tree is n. So n vertices is number of edges will be always n minus 1. So in a tree, face equal 1. Face number of face equal 1. So we see n minus m plus f again equal 2. So if we regard this one as basis case, we have this one equal 2. All right. Now how we obtain a graph? We keep on adding edges. So the important property of a connected graph is any connected graph always contain a spanning tree. So that's a tree with all vertices. So that's very easy to prove. Find a cycle with one edge out of cycle. Eventually, we cannot have cycle at all. The graph is connected and have no cycle. Then it becomes a tree. All right. So later on, maybe I will say a few more words about trees. But anyway, just believe me for the time being. Every connected graph contains a spanning tree. So every graph connected, then it has this one at least. So we can use this one as base. Then the graph can be constructed from this one by keep on adding edges. So if we add an edge, what we have is we form a cycle. So if we add this edge, we form this cycle. So this cycle becomes phase in the plane embedding. So what happens? You will create one more cycle, one more phase, and one with addition of one edge. So each time when we add an edge, once we add an edge, what happens is divide the region into 2. So whenever we add an edge in the region, so it divides this region into 2. So one phase becomes 2. All right. So we add one phase, add one edge, we create one cycle. So these two keep on canceling. So again, this one still maintained. But the consequence of what we do, eventually we still have this one. All right. So that's the intuition of the Euler formula. Actually, you can use this idea, organize it into a proof. Okay. So that helps you get the intuition why Euler formula holds. Now we can use Euler formula to show that planar graph cannot contain many edges. So how can we show that K5 these two graphs are not planar graphs? Of course, we can use topology concept actual embedding. But the easier way actually to count the number of edges. These two graphs have too many edges. So for this purpose, we need a following formula. So this number is very important. It contains at most 3n minus 6 edges. Cannot be more than this. All right. So let's take a look at the extreme case. For four vertices, what the maximum number of edges can contain? Extreme case say 3 is 3 edges. For four vertices, maximum number of edges contained is 6. So that's the extreme case. In the extreme case, each face is a triangle. Each face is a triangle. That's the extreme case. So the graph we obtain is called the maximal planar graph or planar triangulation. All right, so that's referred to planar graph with exactly this many edges. So that's a planar graph with exactly so that's the extreme case. So the maximum number of edges it can contain is this many. All right. So here, if I do this one one is also planar triangulation. I can triangulate. So that's contain maximum number of edges. So how many vertices? 6, 12 edges. So that's maximum possible. If I add one more edge, the graph is not plane anymore. All right. Actually, for this one, we cannot add any edge. If we add one, it will cross. So if add this edge between these two, it has to cross one of the edges. Regardless of how I draw it, if inside, I will cross it. Outside, if I do this, will cross this edge. Okay, so why is this the case? Maximum number of edges 3n minus 6. Proof is extremely simple. Actually, it's extremely simple. Use the handshaking theorem, basically. Okay. So degree sum equals 12, twice the number of edges. Similarly, number of edges equal the summation of face length. So suppose we number the faces, one number of the face number, give it a name, 1, 2, 3, 4. So each face has length. Then if we sum up face length, what we get is twice the number of edges. Because each edge will be summed twice. When we so this face, the two edges will belong to this one, also belong to this one. So each edge counted twice. One from this face, one from this face. So that's why it's important for cut edge. So in this graph, this edge, when we compute the face length, this one will be counted twice, not once. When we compute the face length, this will be counted twice. The confirmation of face length equal twice our number of edges. All right. So that's same as handshaking theorem. If you look at the dual, it's exactly the handshaking theorem for the dual graph. So that's the handshaking theorem. or steel graph, if you like. So that's how we get it. Okay. All right. So that's what we get. Now what? Now the graph is simple graph. The face length, each face contains at least three edges. So this summation, so at most three times number of faces. So that gives us a connection between number of edges and number of faces. Now we can combine with Euler formula. All right. Now what we are going to do is combine this one, so this one is gone. Okay. So this one. Okay. So F can be written equals m minus n plus 2. So that gives us, all right, so that's why we don't need them anymore. Okay. So that gives us the 3m minus 3n plus 6. So 2m, 3m, so that gives m. Let's see, why do I get, should be less 6. Why do I get more 6? Oh, sorry. Face length. Each face contains at least three edges. So this one I reversed. So actually, sorry, I reversed this one. This one at least three F. Each face has at least three edges. So I reversed the direction. Okay, sorry. This one needs to be. Okay. So that's what we get. Number of edges is at most 3 and minus 6. Okay. So now we can use this one to show that K5 is not a planar graph. So how many edges in K5? So n equals 5, n equals 10. Now, use this formula. If 5 here, its m should be equal 9. For any planar graph on 5 vertices, the maximum number of edges is 9. But this graph has 10 edges. So we show this graph cannot be planar graph. So it's much easier than draw it. Actually, we don't need to draw it because the graph is too dense. All right? Okay? Now, how about this one, K33? So can we use the same formula to show that K33 is not planar? Unfortunately, no. For K33, number of vertices equals 6, number of edges equals 9. If we use this formula, we allow up to 12 edges. For 6 vertices, we allow at maximum is 12 edges. Here only 9 edges. So the density condition does not rule out the possibility that this graph is a planar graph. Okay, so what do we do? Actually, we can tight this bound. We can tight this bound. We can tight this bound for this kind of graph. So this in general for planar graph. But now if planar graph has no triangle, if no triangle, Then this number, instead of 3, it becomes 4 because smallest face will have 4 sides, with 4 edges. So instead of 3, we get 4. So you can get this one. All right. Now everything else is same. Here is 4. Here 2m. That will be 4. 4. Here become 8. So then this one becomes 2n minus 4. Okay. So instead of 3n minus 6, we get 2n minus 4. So for 6 vertices, the number will be bring down from 12 to 8. So here is 9, so it's impossible. So use this result, we can show that this graph cannot be a planar graph. All right. Okay. So you see the usefulness of Euler formula and the density condition for planar graph. At most 3n minus 6 edges is important, and 2n minus 4 edges when it has no triangle. All right. In the homework, there are a problem asking for out-planar graphs. Graph is not planar graph. If we can embed the graph on the plane, so all vertices are in the exterior face. So all vertices will be on exterior face. All right, so inside we can have edges, edge crossing. So graph will look like this. This kind of graph. So may have this one. This is called out planar graph. Actually, if we consider embedding the sphere, it's same as one face contain all vertices. It's that exactly same, okay? So in the homework, I asked you to prove the number of edges of an outplanar is bounded by 2n minus 3. Okay, so this, the proof we give here should give you an idea how to do this. All right? Okay, so this one is only going to give us a necessary condition for graph to be planar graph. It cannot fully characterize planar graphs. It happens that planar graph can be characterized merely by the non-existence of these two graphs modular some condition called subdivision. Subdivision of a graph. Subdivision. What we do is insert vertices into edges. To insert vertices. Don't make any new connection. Just insert vertices into edges, or without inserting one, or inserting at least one, or without inserting is all right. So this is called subdivision of G. So original graph is if original graph G, then new graph is subdivision of G. All right. So it's easy to see that if K5 is not planar, is not a planar graph, its subdivision of course cannot be planar. If I add new vertices to the curve, it does not change anything, right? It will not make the graph being planar. Because the curve is still same curve. So it happens that by Klotowski theorem, the existence of subdivision will be sufficient. All necessary is sufficient for a graph to be a planar graph. The Klotowski theorem says Okay, if there is no subdivision of K5 or K3, K33, then the graph is planar. One direction is again trivial. If it contains subdivision of them, of course they are not planar. Typically, as a truncus, then it's often in graph theory. If it contains one of them, of course not planar. So here it says, the beauty is it says whenever it does not contain subdivision, then it's always a planar graph. Of course, the proof is complicated. I'm not going to show it. I will give you one more example to show that Peterson graph is not planar by using this condition. Okay. So this Peterson graph, if we use this formula, if we count the number of edges of this one, it will not work. Of course, we can use similar idea to prove it works, but not these two formulas. We need to use a defined formula. So here I will show you a subdivision of this one contains a subdivision of K33. That shows it's not a planar graph. Okay. So let's see. Let's see. Okay, it's takes some time to find it. I think I found it. Uh, I found it. One, two. Let me take a peek. Okay. Sorry. Let's see. Oh, thanks. It's just that actually here. Instead of this one, I use this one. It's not this one. Okay. So it's this. Messy. So there are two sides of K33. One side is maybe use different color. So this one side, blue one. And red one is another side, these three square ones. The red one will join to each blue one. So this one, this one, this one. So this one, so this blue one in this way, this blue one in this way, this blue one in this way. This one goes this one, this. Maybe I redraw it. Wave the edges actually makes things hard to see. Get the three red ones. This one, three blue ones. So edges. So this one goes like this. So this one subdivision is look like this. Okay, so this one goes to this A, this one, this blue one, this blue one, the other blue one like this. This one goes to like this, and this. The red block is a subdivision of K33. So because this block contains such a subdivision, so the Python block is not the planar block. Okay, sorry, I'm overlearning. I think I will finish here. I will make one or two short videos talking about the trees and five type blocks. I want to add something, a little bit of something. Okay, but basically that should be good enough for homework and exams. All right. So that's it. Okay. For the final exam, I think most likely it will be online. Yes, is considering that now, okay, because of the current COVID-19 situation, everyone worry. Of course, I also worry about this, your health. Certainly, we will not, should not sacrifice your health for sake of final exam, okay? So just be patient. And in the meantime, I really strongly encourage you to prepare for the cheating sheet. It's very important and very useful. That gives you a chance to review course materials and summarize important things. All right, so that will be always useful. Okay. So watch out for anything that may happen in the future from course homepage. If there's any updates, I will announce it on the course homepage. Okay. That's it. Thank you. Oh yeah. Yeah, tutorial next week. Tutor will talk about solution to homework 5. So no tutorial this week, and then next week tutor will talk about that. All right. Trees. If there will be something on trees, we discuss it briefly. Discuss trees. I'll give you something more in a short video. All right. Okay. Yeah, I know that there are no lesson next week, but tutorials will be recorded anyway. You don't need to attend the tutorial at that time. Okay.